Hi, you will not believe what happened to me. It all started with one of my regular research retreats. This is some video that the police took from my phone. As you can see, well, nothing's happening at all, but if you could see something, you'd see there was, nothing was out of the ordinary. There was no indication of what was about to transpire, that Bing Liu would be found murdered in my study. Inspector Petitjean knew that the eyes of the data science community would be on him, and so if he was going to convince a jury beyond reasonable doubt, he would need to produce evidence that was statistically significant. So he set systematically about collecting it. First, he narrowed down the scene of the crime and sent the relevant evidence to the lab. The results came back statistically significant. P equals 0.001. The murder occurred in the kitchen. This allowed him to identify the potential weapons, which again he sent for analysis. And again, a statistically significant result. P equals 0.002. He could now take fingerprints from this murder weapon, having established what it was, and that narrowed down the suspects to only two: myself or my good friend, Bart Hootles. He then took DNA evidence and again sent that to the lab, and again the results came back significant. Bart did it. P equals 0.02. But did he have the evidence to convince the jury? No, he realised that he had a problem of multiple testing. Now let's just remind ourselves what this problem is. So when we do a statistical hypothesis test, we have a null hypothesis, and this is the proposition that we seek to reject. And we want to reject it because we want to be able to accept its negation, the alternative hypothesis. And we're only going to reject it if the evidence that we have is sufficiently unlikely given the null hypothesis. If it is less than or equal to some threshold, we call alpha. Traditionally set to 0.05, and I'm going to assume alpha equals 0.05 from henceforth. All right, so just to illustrate this, Australia has a gambling game called 2 Up. It's a big advantage to have a coin that's biased to heads if you play this game. So suppose I want to find such a coin. I might take a potential coin, toss it 10 times, and then assess the probability that I would have got the number of heads that I get if the coin was unbiased or biased towards tails. And if that's sufficiently unlikely, then I accept it's not unbiased or biased to tails and take it along to my 2-up game, expecting to win. And the test that I use for that is I use the cumulative binomial distribution and the binomial sign test. Right, so I'm only going to reject it if there are 9 or more heads, because the probability will be less than 0.011. If there were 8 or more heads, the probability of getting that outcome is slightly over 0.05. Okay, so that's a single multiple hypothesis test. What happens if we do many of these? Well, each time I'm controlling the risk, but if suppose I was to try this with 100 coins, then every time there's a 5% risk that I will accept one that's actually not biased. And so even if they're all unbiased, I should expect to except about 5 coins. I'll go along to my 2-up game and I'll lose money big time. So it's a bad idea. So what I want to control is the family-wise error rate. And what is this? This is the risk that one or more of the null hypotheses I reject is actually true. Now, statisticians have known about this for a long time, and the classical approach for correcting for this is the Bonferroni correction, where you divide alpha by n. So if I'm doing 100 coins, it's 0.05 divided by 100. A more powerful alternative is the home test, where I do all my coin tosses, I evaluate all my null hypotheses, I get my p-values, I sort them in ascending order, and then I keep rejecting them in a stepwise fashion, at each time testing against alpha divided by the number of remaining hypotheses, and I stop as soon as I can't reject one. So let's see what happens if I apply the home procedure to Inspector Petitjean's case. Well, we have a total of 9 null hypotheses that were investigated. First one, the lowest p-value, 0.001, is less than alpha 0.05 divided by 9, so we're fine. Second one, 0.002, is less than 0.05 divided by 8. We're fine. But 0.02 is not less than 0.05 divided by 7, so he's not going to be able to use this technique to convince the jury. So is the game over? Well, no. This is a special type of multiple testing scenario. It's what we call a hypothesis stream. So in the classical multiple hypothesis testing scenario, you just have all of your hypothesis tests and you consider them all at once. In a hypothesis stream, hypotheses are considered over a period of time, and you want to make decisions about rejections before you've encountered all of the hypotheses you want to consider. So you can't apply the classical techniques because you don't know how many there are going to be, which the Bonferroni or home corrections require. Right, so we're encountering groups of, so in the scenario we're going to be looking at groups of null hypotheses. Each step we're going to reject one and then proceed on to the next ones. Right, and their existing approaches ignore the number that there are at each point in time. And we're interested actually in a specific case of this, which we call a hypothesis cascade. So here, the one we decide to reject affects the next hypotheses considered. Right, so consider the case where Inspector Petitjean was able to reject the null hypothesis that the murder did not take place in the kitchen, so he could conclude it took place in the kitchen. That enabled him to narrow down the weapon. Identifying the weapon allowed him to narrow down the suspects. So the hypotheses to be considered at the next stage depended on the rejection at a particular stage. Now you're probably sitting there thinking, well, this is actually just standard old statistical sequential hypothesis testing. No, it's not. So the statisticians have considered a case where you're doing something like this, but you only consider one hypothesis at a time. We're considering multiple, but only rejecting one. And it's not a standard gatekeeper procedure. With gatekeeper procedures, you consider whether or not to reject all of the null hypotheses you're considering at one point in time. We only consider one. Okay, so here's the only formula I'm going to present to you. In in multiple testing corrections, we deal with what's called the family of null hypotheses. This is all the null hypotheses that we're considering. Of those, we are going to reject some subset. And of all the family, some subset is going to be true. And we want to not reject any of the true ones, so we want the intersection between those sets to be empty. And to control the family-wise error, we want to ensure that the probability that they're not empty is less than or equal to alpha. So our risk. And what we show in our paper is that our procedure is able to control that risk at any given level. So instead of just having one family, we have a whole lot of sets of null hypotheses, each of which we call f subscript I, so the subfamily considered at time I. And at each step, we're going to reject the one that is most unlikely. So when I was tossing the coins, the coin that got the most heads. And what we show is that the cumulative risk is no greater than the sum of the minimum p-values, the p-values of the ones we reject, times the pool, the size of the pool from which we rejected it at that time. Let me show you, try to give you an intuition behind this. So remember, if I toss 10 coins, then the probability that I will get 10 heads is less than or equal to 0.001, 9 or more heads, less than or equal to 0.011. Now suppose I want to increase my chances of getting a biased coin. I might take 2 coins, toss them each 10 times, and then take the one which turns up heads the most. What would be the probability that one or both of them would land heads 10 times? It would be no greater than 2 times the probability of any one of them doing so, so 0.002. Probability that one or both of them would land 9 or more times, no greater than 0.021. Okay, so I might do that, and suppose I get a coin that lands 9 times heads. I might go on and take another 2 coins and do the same thing. Probabilities there are going to be the same. Now, remember, I want to control family-wise error. So that's the probability of one or more of them being rejected in error. So if I've rejected the first coin in error, so if it actually was unbiased, then I've committed family-wise error. It doesn't matter what happens thereon. Now I only need to worry about the possibility that the second one might be unbiased and control the risk conditioned on having tossed a fair coin 9 more times, that I would have committed family-wise error under this procedure. And that, you can see, cannot be more than the sum of these probabilities. And so I can continue summing the probabilities as long as they do not exceed alpha. How powerful is this technique? Well, here we conduct a Monte Carlo simulation, 3D plot. The depth is the subfamily size, so the number of coins I'm tossing simultaneously. At the rear, there's only one null hypothesis at each step. At the foreground, there's 1,000. Horizontally, from right to left, on the right-hand side, your left-hand side, your right-hand side, there is the proportion, right? So horizontally we have the proportion of null hypotheses that are true. So on the right-hand side, they're all true. On the left-hand side, none of them are true. And then the vertical plot is the family-wise error observed. You can see the family-wise error is highest at the rear rightmost point, which is where at each step we just have one null hypothesis and all the null hypotheses are true. Why is it exactly 0.05 then? Well, we commit family-wise error if and only if we reject the first null hypothesis, and there's 0.05 risk of that. The family-wise error decreases as the subfamily sizes increase. Why is that? Because in our Monte Carlo simulation, the null hypotheses were independent of each other, and we're controlling for the risk that the rejection regions are mutually exclusive, which is the worst possible case. And as the proportion of null hypotheses that are true decreases, fairly evidently the risk of family-wise error decreases. If there are no true null hypotheses, we can't reject a true null hypothesis. Now, I know what you're almost certainly thinking. Well, nice proof, but isn't this just some academic exercise that Francois and Geoff dreamt up just so they can get yet another KDD paper? Well, no. Actually, this has been an open problem in statistics for at least 2 decades. Well, if the statisticians have realised for at least 2 decades that this is something worth solving, why haven't they solved it? Well, as the statistician with whom we are working to develop a version of this for publication in a statistics journal says, our approach is unconventional. In fact, I think the real answer is that it's the frequentists who do statistical hypothesis testing, and the reasoning you require to reach our procedure requires the use of conditional probabilities, and they look on those with suspicion because they've got a faint whiff of Bayesianism about them. Okay, so why is this something the statisticians have been interested in for a long time? Well, because it solves an important problem. The reason we came to this is because we've been working for some time on scalable graphical modelling, and what we want to be able to do is to take some set of variables and look at all the potential interactions between them, starting with a model which has no interaction, consider all the possible models that have one interaction, take the interaction for which there's the strongest evidence, so the p-value for the null hypothesis is lowest, reject that null hypothesis, accept the model that includes that interaction, and then continue the process, now considering all models with 2 interactions, including that first one. So clearly it's a hypothesis cascade. Does it have any value in practice? Well, this is just one of the benchmarks where we've applied this. So this is a study of elderly people with various medical variables recorded, and the black shows what the best in the state of the art was able to find without our technique. With our technique, we're able to pick up 3 more very subtle interactions. Okay, so I know what you are all really interested in. Did Inspector Petitjean manage to get the jury to convict Bart? Well, let's take you through the evidence. There were 4 scenes of the crime. Probability for the minimum, so the minimum probability, which you could reject a null hypothesis, 0.01. There were 4 things considered, so the cumulative probability is 0.004. that led us to have 3 weapons. Minimum p-values 0.02. That adds 0.06 to our cumulative probability, giving us cumulative probability of 0.010. And now to the point that really counts. Can we convict Bart? P equals 0.02. 2 suspects, that adds 0.04, which gives us the magic number 0.05, which just squeezes in. We can put Bart away. I invite Inspector Pettyjohn to join me on stage because I know that you're probably more interested in asking questions of him than me. Thank you.
So if I understood correctly, the order that you do the hypothesis testing does not matter in your approach, and I don't know if I'm correct in that. Do you have cases where you think that the order in which you check its hypothesis would actually matter?
So the question was, does the order in which you consider the hypotheses matter? And the answer is yes, critically. Right? So we're doing a stepwise process, and we're going to stop as soon as the cumulative probability exceeds whatever alpha we've selected. Right? So if the very first one had a p, the minimum p was greater than alpha, we'd stop there. Right? But if that one was the 5th one, then we might go up to rejecting 4.
All right. So in that case, then how do you choose the order?
How do we set the order?
How do you choose the order? If the order affects the result, how do you know which order to go in?
So we don't choose the order. We're taking some situation where null hypotheses are coming to us. So in our, right, so the only real world, I don't think this is going to be very useful in murder investigations, just to let you in on a secret. I think the real application for this that we know of is the stepwise model selection. And there we consider, first of all models that have one interaction. Right? Then, having selected one of those, we consider all models that have 2 interactions, including that one. So the order is the size of the model.
All right, thank you.
So we think there are other applications, but we don't have a clear demonstration that they really are.
Other questions? Thank you for your talk. I think your problem is you fit in a stream of the hypothesis and you determine when to make the decision. Can I understand like that?
So the question was, is our problem that we consider a stream of hypotheses and we decide whether to make a rejection? So it's a little more complicated than that. So our situation is that we have a stream of collections of hypotheses. And at each step we decide whether to reject one of the collection we have at one point in time.
My question is, have you considered the non-stationary case? For example, the probability they can change according to time for once.
So have we considered a non-stationary case? So I'm not sure where that would come into it. So it certainly doesn't come into our application, which is stepwise model selection.
Okay.
Yeah, so perhaps you're thinking of the situation you have in A/B testing, where what you're interested in doing is considering at one point in time whether or not you should reject the null, whether or not you can decide you're not going to reject the null hypothesis, and so cut the experiment off, and then continue collecting more evidence until such a point at which you decide you can reject it. And we're not doing that. We're not considering it the same null hypothesis at repeated steps in time. We're considering different null hypotheses at different points in time.
Okay, thank you.
Thank you.
Hey, would it have made a difference if, for instance, there were two locations that were under the threshold in the first stage? Yeah.
Okay, so the question was, would it have made a difference if there were two under the threshold? So there are multiple things which may have been, multiple directions in which you might take that. So it doesn't affect the probability of family-wise error. There's a boundary case where you have two p-values that are equal, and we haven't actually stated this in our proof, but there you have to select between them randomly. If there are two which are under alpha, you're only going to reject the lowest one. It's important that you're rejecting the lowest one. If you weren't rejecting the lowest one, you would have to have some criteria other than the p-value on which to be rejecting it, and you'd have to then use its p-value instead of the p-value.
I guess this is where the investigation example and the model selection example diverge. In the investigation example, then you would have considered the weapons from both of the locations that were below threshold. From the model selection, since you're selecting the max, or something like that.
So we don't seriously think that you'd apply this in murder investigations. Let me just make that absolutely clear. But think of what it would have required if there was a p less than 0.05, that poor old Bing had been murdered in the kitchen, and a p of less than 0.05 that had been murdered in the study. That would have meant that the probability, given the evidence that he had not been murdered in the kitchen, was less than 0.05, and the probability that he had not been murdered in now, what am I saying here? I'm confusing myself. In the study was less than 0.05, and that doesn't seem like an inconsistency at all.
Because I think it does have applications for things similar to model selection. So for instance, in my model selection, that's just a greedy selection is one thing, but you could have a beam search style.
No. So it's absolutely critical that you don't just select the ones that are less than alpha. Right? The whole thing would fail if you tried doing that. Right? You could decide in advance, I'm going to reject k at each step, and you could then revise it to do that. Or you could have some other selection criteria to decide which ones to select, as long as it was not to do with the p-values. Right? So as long as it was not, I'm just going to keep accumulating them as long as it's less than alpha. Because then implicitly, you're considering the one which takes you over alpha, and at that point you've incurred the risk.
So sorry, we need to keep on schedule. So let's thank the speaker again. If you have further questions, you can